This is a screencast for section 2.3, example 9. Are you tired of designing boxes yet? Because I sure am. The Dixie Packaging Company has contracted to make boxes with a volume of approximately 484 cubic inches. So squares are to be cut from the corners of the 20-inch by 25-inch piece of cardboard, and the flaps are going to be folded up to make an open box, similar to what we did last chapter. So what size squares should be cut from the cardboard? So in last chapter, we would find the maximum volume the box had. Now we're trying to find the exact volume, 484 cubic inches. So I know that the volume of a box, the volume of a box is going to be length times width times height. In this specific case, 484 is the volume I need. The length is going to be, 25 inches minus the 2 x's we're going to cut off of each side. So 25 minus 2x. The width is going to be 20 minus the x on either side, so 20 minus 2x. And then the height, once you fold those up, is going to have a height of x inches, basically the dimension of the corner that I cut out. So now, in order to find that, I'm going to use my calculator. I put in the calculator 25 minus 2x times 20 minus 2x times x into y1, and then I put into y2 484. Now I'm in a graph, and this window is definitely not right yet. I know that my I can see part of the graph right there. That's good. But I know my y values are going to be probably close to 500. So I'm going to set my window, my y max, just to get a frame of reference. I'm going to go with 550 so I can clearly see the line that I'm looking for. So I hit graph. Oh, I can actually see 2 of the intersections. Now I know that there are 3 x's in this function, so this is a cubic function, which means both end behaviors are not aimed down. One is going to be aimed down, the other one's going to be aimed up. So I'm missing some information over here. So I'm going to set my x max to be a little bit higher. I'm going to go, let's go 50. That's probably too far, but I'll try it anyway. Yeah, I probably could have gone with maybe 30. Right now I'm having a hard time seeing that, the dimension or the intersection over here. Let's change my x min to -2, my x max to 20. That's better. So now I'm going to find the intersections of all 3 of those points. So now that I found the 3 intersections, I can figure out, I can analyze what they mean. So this first intersection means that if I cut out a 1.2 inch by 1.2 inch square from each corner of this piece of cardboard and fold up the sides, the volume is going to be 484 cubic inches. Well, a box that only has a 1.2 inch height seems like it really wouldn't hold much, so I guess it depends on what you're going to be putting in these boxes. If you're going to be putting in like maybe puzzle pieces, I mean those are flat, so 1.2 inches might be okay. This second intersection, 6.87, so I could cut out 6.87 inch corners from 6.87 inch squares from each corner. Fold those sides up and I would get a 484 cubic inch box as well. Now if I fold about a 7-inch side from, or a 7-inch section from each side, that's going to take up about 14 inches, which means on this side, so out of the total 20 inches, 7 is going to be taken up on the one side, 7 is going to be taken up on the other side, totaling 14, which means I have 6 left for the middle. So that's a pretty square looking box. I mean, it's going to be rectangular because on this side, it's going to have, 6 inches from this side and 6 inches from this side. So actually, no, 7 and 7. So that's 14. That's going to be about 11 inches left in the middle. So that's a good size box. You could put maybe a toy in there, depending on what kind of object you're packaging, maybe a pair of shoes, I don't know. Then this last one creates a problem though, because if I cut out a 14.41 inch square from each corner, I'm going to cut 14 inches from this side and 14 inches from this side, which means I need a total of 28 inches out of this box, which doesn't exist. So this is not in our relative domain. We cannot physically cut that out of the box. We would have some sort of weird black hole thing going on. So my options, question says, what size squares should be cut from the cardboard? So my options are a 1.22 by 1.22 inch square, or a 6.87 by 6.87 inch square. They will give you two very different shaped boxes, but at least they would create a reasonable height and length and width, not like this last option that would cut too much out of the box. The now try problem is number 67. Same kind of situation as example 9. There are squares of width x that are removed from a 10 centimeter by 25 centimeter piece of cardboard, and the resulting edges are folded up to form a box with no top. Determine all the values of x so that the volume of the resulting box is at most, at most 175 centimeters cubed. Well, volume equals length times width times height, but this time we don't have an exact volume we want to equal. We have a maximum volume. So my maximum volume is 175. That has to be greater than or equal to, so that is the highest. The rest of it has to be less than. So the biggest number, the alligator mouth, is going to go to the 175. 175 is greater than or equal to, let's see, we've got the 10, this should say centimeter side. 10 centimeter side minus the 2 x's we're cutting from each edge. The 25 centimeter side minus the 2 x's we're cutting from each edge. And then the height, which is x. Length times width times height. So now I'm going to use my calculator to find out the x values that will make this true. I'm going to find the x values that will make this equal. So I put the original function the right side in y1, the left side in y2. I found a window. So I found the 3 intersections, and now I'm going to, see, it's not as easy as the last problem in that I just write down the x values. Those are the dimensions that make the problem true. Well, first of all, this, we cannot cut out 13 centimeters from each side of the cardboard because we only have a 10 centimeter stretch for the width. So we're going to cross out this option. The highest amount that I can cut out is 5 centimeters from each section. So what I'm looking at on this graph here is a maximum volume we can hit of 175 cubic centimeters. That's right here. So when the y values are below that line, we're okay. This is not what I want out here because we said that we can't cut out pieces that are too big. The maximum piece we can cut out is 5. The maximum length we can cut out is 5 because of this 10 centimeter stretch. So that's right here. So anywhere the volume is below 175, but of course still positive, we have viable solutions. So I can cut out anything between 0 and 0.93. So x values 0 to 0.93, plus I can also cut out, let's see, anywhere from 3.64 to 5 on the x-axis. So my x values can be anywhere from 0, it has to be greater than 0. We can't cut out 0 because otherwise we won't have a volume of a box. Anything bigger than 0, up to and including 0.93, Now, for x values greater than 0.93 though, so that for this section, the volume is going to go above the 175 mark. Now, starting at this intersection, which we found down here, 3.64 will give us a volume of 175, which is fine, all the way to, but not including, 5. If we cut out exactly 5 centimeters, we won't have a width dimension. It would be 0. So we cannot include 5. So x can be in between any of those intervals in centimeters because those are the x values that create a volume that is positive but also lower than 175 cubic centimeters, but that are not included in, or that can be included in our relative domain. They can actually be cut out of the box.